Hi everyone, welcome to this SynCon presentation where I will be talking about side-channel attacks at the age of deep learning. So my goal during this talk is to give an overview of how deep learning is really changing the way we perform side-channel analysis of cryptographic implementations. So before we get started, just a few words about myself and about eShard. So my name is Benjamin. I work as a security engineer at eShard. eShard's mission is to help companies mastering the security risk in embedded devices. And for that, we provide different types of services. We provide penetration testing services, but we also provide training and we develop security tools. So our team covers the different layers in security. We have people working more on cryptography and on the hardware side. And for that, we have a flagship software called Dynamic, which is a data science platform to perform side-channel attacks and fault injections on cryptographic implementations. So as you can see, this is a tool that I will use today for this talk on deep learning applied to side-channel. And we also have people working more on reverse engineering and on the security of mobile applications. And for that part, we have a new tool called ES-Checker that we are introducing during the SynCon conference. So for people who might be interested in that, I will just say a few words about this new tool. So ES-Checker is a tool to help businesses safeguard their mobile applications by automatically validating that the security protections of the app are functional. So the thing is, without the right level of protections, mobile applications, they are vulnerable and can be targeted by cyber criminals. And so this can be prevented by ensuring that the app protection shield is always functional. And so ES-Checker provides with a series of tests and it provides a comprehensive range of static and dynamic tests which are based on OWASP recommendations. All these tests can be automatically run within your CI/CD pipeline. And so ES-Checker provides an efficient and cost-effective solution for people to run comprehensive security audits on their app and get protection recommendations. Okay, so now let's dive into today's topic. So if we look at cryptography today, we have algorithms that are theoretically unbreakable. If we take a plain text and we encrypt it with a cipher like AES, for example, even if the ciphertext is intercepted, we know that with just the knowledge of this ciphertext, it is impossible to recover the original message because the encryption is secure. But in practice, what happens is that these cryptographic algorithms, they are executed on devices, and these devices leak information through multiple channels that we call side channels, and this can be exploited to recover secret keys. Common channels that we usually can exploit are, for example, the time execution of the algorithm, the power consumption of the device, or also the electromagnetic emanations of the chip. So the problem is not really on the algorithm itself, which is secure. The issue is on the endpoint device that is executing the algorithm and which leaks information. And because devices leak side-channel information, there is always a risk, especially in the context where the device can be accessed by the attacker. So in side-channel, we don't try to defeat the security of the algorithm itself. What we do is to attack from the side, and we target the implementation of the cryptographic algorithm, which is executed on a device, and we exploit the leakages of this device to recover the secret key. So in this presentation today, I won't have time to describe precisely how side-channel attacks work, but I will try to make a quick summary. So the idea behind side-channel attacks is to exploit a relationship between the data manipulated by the algorithm and the side-channel signal that we collected from the chip. And so for that, we usually collect a lot of traces corresponding to several executions of the algorithm with inputs that are different from one execution to another. And after that, we use a statistical distinguisher to detect and exploit the relationship between the data and the signal. So the first attack you will usually find in textbooks is called the correlation power analysis, or CPA in short. And this attack uses correlation as a distinguisher. The idea behind CPA is to guess the value of the key to make some predictions about intermediate values that are manipulated by the algorithm. So after that, we use correlation to measure whether or not the predictions that we made are correct. And we simply select the key guess that leads to the highest correlation. So here we can run an example of CPA in Python. We have a data set here composed of multiple traces corresponding to AES encryptions. And below, we define an attack object where, as you can see, we use the CPA distinguisher to exploit the leakages. And so if we run this attack, as a result, we can see that for each byte of the key, there is a specific value which leads to a high correlation. And this is a value actually that we will select for the key byte that we want to recover. So here it's a very straightforward attack. We are collecting data and we are using a statistical distinguisher like, for example, the Pearson correlation to extract information about the secret key. So to build more complex and powerful attacks, we can leverage techniques from machine learning. And in this case, we have a methodology in two steps. First, there is a learning phase. And during this phase, we will use a machine learning algorithm to build a model that will characterize the leakage of the chip for all the possible values that a secret target can take. And then there is the attack phase where we use the machine learning model that we built to infer some information about the secret value corresponding to a trace that we want to attack. So during the learning phase, what we want is to build a classifier that is able to classify traces based on a secret value. And during the attack phase, we want to use this classifier to recover the secret information from a trace that we want to attack. So for that, once the classifier is trained, we can give a trace as input to the model, and the model will tell us to what secret value this trace corresponds. So for this kind of machine learning attacks, the methodology is always the same, and the only parameter that changes from one attack to another is what machine learning algorithm do we use to build the classifier. So in the state of the art, you can find several techniques with different types of machine learning algorithm and different types of classifier. Historically, one of the most famous techniques used in sidechannel is the so-called template attack, where leakages are characterized using multivariate Gaussian distributions. So it's a very simple type of model, but in many cases it's efficient because side-channel leakages usually follow Gaussian distributions. But because the model is very simple, there is also some limitations. For example, there are some types of leakages that cannot properly be characterized by this kind of models, and also sometimes it lacks some flexibility. And so later on in the presentation, we will see how deep learning actually provides some improvements compared to these previous attack methods. So now if we look at the evolution of machine learning algorithms, since 2014, we can observe a clear trend where deep learning has progressively become dominant for many applications in machine learning, especially for everything which is related to data classification. Today, deep learning usually outperforms other techniques. And what is interesting with deep learning and neural networks is that these techniques, they have been actually around for more than 30 years. But the whole thing started to take off only in the second half of the 2010s decade. And this comeback actually can be explained by multiple factors, but the two main factors that we usually are listed to explain this comeback are the following. So first, there is the increase of computational power, especially the amount of operations that can be performed on recent GPUs and other dedicated hardware. And this makes possible to train bigger and bigger network. And as a result, these networks can achieve better and better accuracy. And the second point is a faster and faster access to bigger and bigger data sets that we can use to train also these big and large neural networks. So these two factors and other factors can explain why suddenly deep learning became dominant. So there is a clear trend in machine learning, and following this trend in machine learning, the sidechannel community also started to investigate the potential applications of deep learning for sidechannel analysis. So there was the first publications about that around 2016, and the first publication demonstrated a clear interest of using deep learning and neural networks. The experiments in this first papers show that deep learning usually outperform previous attack techniques. And so since then, we have seen many articles presented every year in security conferences. And it's definitely one of the most active topics today in sidechannel. Okay, so now let's take a look at how deep learning can be applied for sidechannel analysis. So in my notebook today, I will showcase an example where we will build a neural network that is able to classify traces collected from a device based on a sensitive value which is computed during the AES encryption. So in this example today, we will target a specific value computing during the algorithm, which is the output of the S-box operation at the first round of the AES. It is a sensitive operation because this operation involves the master key of the encryption. And so we want to build a neural network that is able to classify traces based on the value of this sensitive target. So I don't go in the details of the cryptanalysis part, but the idea is that if we have a neural network which is able to predict this sensitive value for several traces, then this knowledge can be exploited with differential attacks to recover the secret key. So here we will target only one bit of the S-box output, and we want the neural network to classify the traces based on the value of this targeted bit. So here below we have a data set which is composed of 10,000 traces corresponding to 10,000 encryptions with different inputs. And here, this is what we call a label data set, meaning that for each trace of the data set, we know the inputs of the encryption, so meaning the plain text and the key. This means that we can assign a label for each trace, and here the label will correspond to the value of the bit that we target. Okay? And below here, for our neural network, we define a multi-layer perceptron, which is a simple type of neural network with linear layers which are connected together, and between linear layers there is activation functions that provide non-linearity in the model. So here, the MLP is composed of 4 layers of 50 nodes each. The input of the network is composed of 400 nodes, which correspond to the 400 time samples that we have in the input traces. And the output of the network is composed of 2 nodes. And this is because in this case, we want to predict the value of a single bit of the S-box output. So we have 2 output nodes, one output for the targeted bit being equal to 0, and one for the bit being equal to 1. So in practice, it's also possible to predict more bits if we want. For example, we might want to predict a full byte, so 8 bits. And in this case, we will have just more outputs. We will have 256 outputs in the network, one output for each possible value of the targeted byte. But so here, today, we keep things a bit simple. We will target just a bit of the value, and so we have 2 output nodes. So we have defined our network. Now we can train it. As we have a labeled dataset, what we can do is just apply a supervised learning method. We feed the network with the traces, and for each trace, we indicate to the network what is the corresponding bit value so that the network can learn to classify the traces based on the targeted bit. Here you can see in live the evolution of the training with the accuracy and loss metrics. The accuracy on the left plot measures the proportion of traces that the network is able to properly classify. And so we can see that over time, the accuracy increases. The accuracy starts at around 50% when the network is not trained. And this is just a probability to successfully classify inputs with 2 labels at random. But over time, we can see that the accuracy increases, which means the network is learning. And at the end, we can see that the training, at the end of the training, the accuracy reaches a level of around 65%, meaning that the network is able to properly classify 65% of the traces, which is already better than a random guess. And so once the network is trained using a labeled dataset, we can use the network to predict the value of the secret information from traces that we want to attack. For that, it's simple. We just pass as input to the neural network a trace that we want to attack, and the network outputs 2 values, one corresponding to the probability that the traces matches with an encryption where the bit is equal to 0, and the other one corresponding to the probability that the sensitive bit is equal to 1. And after that, if we take a separate dataset on which we don't know the value of the key, we can use a network to predict the value of the sensitive bit for different traces. And using differential analysis, we can recover the corresponding byte of the key. And for that, we don't need to reach a perfect accuracy. As you saw, we had an accuracy of only 65%. But as long as the network is able to properly predict the bit value for some traces, it is enough information to break the implementation using differential analysis. So here we saw this is a standard way to apply deep learning to perform differential side channel attack. The methodology is pretty much the same when you use other machine learning algorithms, but here what is really interesting with neural networks is that you can leverage the advantages of deep learning. First, with deep learning, what is very interesting is that you have the freedom to design your network, and so you can build more complex models. And what is really interesting is that you can adapt the network architecture to the dataset that you target. And later in the presentation, we will see a very interesting example of that with CNN, with convolutional neural networks. And in general, what is interesting is that we can leverage all the work that is done in the deep learning field, where many techniques and architectures are designed, and we can reuse all this work for side-channel analysis. Okay, so one other interest that we can mention is that neural networks can naturally detect and exploit multivariate leakages, which is something that most of the other techniques cannot do by default. So a multivariate leakage is a type of leakage which is composed of two or more components splitted over several instances in time. An example of that is, for example, when developers implement what we call a masking countermeasure. Masking is a countermeasure where sensitive values like the keys, for example, are split into multiple shares that are manipulated separately. So it protects the implementation against side-channel attacks because the sensitive value itself is never manipulated by the algorithm. The algorithm actually operates on the shares instead. So the simplest example of that is when a sensitive data is split into two shares, a mask and a masked value. And in this case, if we want to perform an attack targeting this protected value, what needs to be done is to identify and combine the leakage of the first share with the leakage of the second share. So this is what we call actually a second order attack. It's something that is usually quite challenging to do because the two leakages must be identified first, and then the leakages must be combined together before the attack is performed. What is nice with neural network is that during the training process, when the gradient descent algorithm is applied to optimize the network weights, the network can automatically detect the different shares leakages and combine them together. So it means that neural networks, they are naturally able to exploit this type of multivariate leakages. And so it's a huge plus compared to other techniques. So let's take an example of that. Here we have a data set which corresponds to a masked AES implementation where the sensitive bytes are split into two shares. At this stage, we don't know where the leakages of the two shares are located, and we also don't know how to combine them. But so what we can do is to take a neural network, for example, a MLP, like in the previous example, and we can run a training exactly like in the previous example. But this time, in addition to the accuracy and loss metric, we will observe another metric, which is called the sensitivity of the network input. And this metric indicates which input nodes contribute the most to the classification of the input data. Okay? So if we run the training with this metric, what we can observe is that the network during the training automatically detects and focuses on two specific areas which actually correspond to the time samples of the two shares of the data that we target. So the network detects the two shares and combine their respective leakages inside the network to classify the input data based on the combined information, which is the sensitive information that we want to exploit. So it's very powerful. Here, everything is automatically done by the neural network in comparison to other methods where the leakage combination must be done before the attack. It must be done manually by the attacker. Okay, so another example that we can study is how we can use specific network architectures like convolutional neural networks, for example, to solve some problems from side-channel analysis. One common problem that we face in side-channel is what we call signal desynchronization. And so this happens, for example, when we collect multiple traces from an oscilloscope. Most of the time, there is a time desynchronization between the different traces, meaning that from one trace to another, the same time sample does not correspond to exactly the same leakage. And the effect of desynchronization is that it adds some noise to the signal, and it reduces the efficiency of the statistical side-channel analysis. So here you can see an example of what is the impact of desynchronization on an attack that uses the correlation distinguisher. At the top, you can see the overview of the traces used for the attack. And at the bottom, you can see the result of the attack with the corresponding correlation result. So at the beginning here, there is no desynchronization, and we can see that the attack works pretty well because for one of the key guesses, we observe a very high correlation. But now what we can do is see what happens if we artificially add desynchronization to the signal. So here, at each step, we add one time sample of desynchronization to each input trace. And we can see that very quickly, it reduces the efficiency of the attack because the correlation becomes smaller and smaller. And at the end, with just a few samples of desynchronization, it becomes impossible to recover the secret key byte. So the goal in sidechannel is always to reduce this desynchronization. And so there are many techniques to do that. Most of the time we use techniques from signal processing that we use to realign the traces and reduce this effect. But again, this is a processing that usually must be done manually by the analyst. It can be very time consuming, it can be challenging because it requires to analyze the signal and to adapt the alignment procedure to the dataset. So now I want to present how convolutional neural networks, they provide a very nice solution to this common issue in sidechannel. Okay, so convolutional neural networks, or CNN in short, it's a popular type of network architecture that was originally designed for image classification. And the core of the CNN architecture is a combination of two types of layers. The first type of layer is convolution layers, where a convolution kernel is slided along the input data, and where the weights of the convolution kernel are actually the trainable parameters of the network. And the second type of layer is a pooling layers, where pooling operator is slided along the output of the previous convolution layer, and this pooling layer produces a local summary of the convoluted data. So a CNN is composed of a series of convolution plus pooling blocks chained together, and at the end of this convolution and pooling blocks, there is a series of fully connected layers or linear layers that are used to classify the data into the different classes. Okay? So now we can have a look at how a CNN transforms an input data into what we call abstract features. So if we take the example of image classification, in image classification, we start with a picture, which is composed of a single feature if it's a black and white picture, or is composed of three features, three color features, red, green, and blue, if we use a color picture. And so in the input image, the size of each feature is quite large. In the input image, the image is basically composed of hundreds or thousands of pixels in each of the color feature. And what happens is that the CNN will transform this small number of large features that compose the input image into more and more abstract features that become smaller and smaller the deeper we go in the network. Okay? So you can see in this diagram the deeper we go in the network, the higher the number of features that are outputted by the convolution layers. And these features usually become smaller and smaller because at each step we apply a pooling operation that compresses the information and it reduces the dimension of the features. So at the end of the convolution blocks, what we get is a large number of usually pretty small compressed features that we call abstract features. And at the end of the network, the final layers, the fully connected layers, will classify the data into categories based on the value of these abstract features. So the combination of convolution and pooling layers in CNN, it offers a very interesting property to these networks, which is a translation invariance property. This is something that is quite simple to illustrate and understand with image classification. When we build a CNN to classify images, we want that the network is able to detect and classify the object whatever its position in the picture. And this is a property which is naturally provided by the CNN architecture. If we look at the convolution layer used in CNN, the convolution kernel is slided along the input data and along the features inside the network, which means that the relevant information is always captured whatever its position in the data. And the second important point is that the pooling operations are used as a compression method, and it also reduces the effect of the original translation the deeper we go in the network. And so thanks to this property, it means that CNNs are also naturally efficient to classify side-channel traces that are desynchronized. And it's for the same reason as in image classification. Even if the relevant information is slightly shifted from one trace to another, the CNN architecture will naturally be able to capture this information and properly classify the traces. And so it's very, very interesting because it means that, again, in this case, everything is done by the network itself. We don't need to resynchronize and realign the traces before the attack. Everything is done by the network, and CNN convolutional neural networks, they are able to handle this kind of desynchronization. Okay, so now let's observe this translation invariance property on a real example with side-channel traces. So here we have a convolutional neural network with 4 convolution blocks, and this network was trained on a desynchronized dataset. So we reload the parameters of this trained network, and below here we have a small widget that we will use to observe the translation invariance of this network. So with this widget, we are able to observe the features at the different layers of the CNN. Okay? So we start at the input of the network, and here we display 2 input data. We display in blue an input trace, and in orange we display the same input data, but that we artificially desynchronize. So in orange, it's the same trace as in blue, but just shifted 10 samples to the right. And what we will do is to observe how the network processes these 2 inputs across the different layers. So if we observe the output of the first convolution block, we can observe that basically the layer outputs pretty much the same information for both traces. And this is what we expect from what we explained earlier. Because of the convolution kernel, which is slided along the input data, it captures pretty much the same information for both input traces, but with just a small offset. But what is interesting is that this offset between the convoluted features will gradually decrease the deeper we go in the network. And this is because at each step we will apply a pooling operation, and this pooling operation will compress the information and reduce the dimension of the features. So if we observe the output of the second convolution block, again, we can observe that the data is pretty similar for both inputs. Because of the pooling operation, we can observe that there is actually some information loss between the two data, but the information is pretty similar. And here we can observe that the offset between the two information was clearly reduced. We started with an offset of 10 samples in the inputs, and after the second layer, we only have 2 samples of offset between the two signals. So here we are using a pooling layer with a window size of 2. So we divide the dimension by 2 at each layer, meaning that the original offset is reduced by 2 at each layer of the network. Okay. So if we look at the output of the third block, we can see that there is still some loss because of the pooling operation, but the two signals are pretty similar, and at this stage the original offset almost disappeared. Okay. If we look at the output of the last convolution block, this time the original offset completely disappeared, and the two signals are still pretty similar. Let's say the convoluted features for the two signals are pretty similar, and the original offset was completely removed. So here we started with two signals that were desynchronized, and what we can see is that the output produced by the convolution blocks are very similar for both signals, and so after that it's pretty simple for the last layers of the CNN to classify the two inputs in the same categories, because the two inputs have pretty similar abstract features at the end of the convolution blocks. So this example illustrates how the translation invariance works with CNN, and why it is able to efficiently process side-channel traces that are desynchronized. And so, as I explained earlier, because desynchronization is one of the biggest challenge in side-channel, it's very interesting to have neural networks like CNNs that are able to handle desynchronization and still be efficient to classify side-channel traces. And so it's very interesting because here everything is automatically done by the network. The attacker, the analyst, does not need to resynchronize the traces manually before the attack. Okay, so finally, I just want to mention a few other techniques that for me illustrate why deep learning is opening the door to pretty exciting possibilities for side-channel analysis. So the fact is, deep learning is a very vibrant field. There are many new techniques being published almost every day in this field. And what is great is that many of these techniques, they can be reused for other applications in other fields, like for example for side-channel analysis. So the first example I wanted to mention is the use of autoencoders for denoising side-channel traces. So autoencoders is a type of neural network that is composed of two parts. The first part of the network is called the encoder, and it compresses the input into an encoded form, which is of a lower dimension than the input data. And then the second part of the network is what we call the decoder, this part reconstructs the original signal from the encoded data. So the goal when training an autoencoder is to get a network that is able to efficiently reconstruct the original input from the compressed encoded data. And so there are many applications of autoencoders. One of them is denoising autoencoders that are used to remove or reduce the noise from an input data. And so exactly like desynchronization, noise, it's a very common issue in side-channel analysis. When you collect signal from a device, you always want to reduce the noise level so that attacks are more efficient. And so as you can see below, I listed one article published in 2020, which explores the application of denoising autoencoders for side-channel analysis, and it's pretty interesting. And so the second example I wanted to give is the usage of generative adversarial networks to generate artificial side-channel data and improve the efficiency of training when working on side-channel datasets. So GANs, it's a special type of network architecture that can be used to generate artificial data from real data examples. So in a GAN, you have actually two networks that are competing against each other. You have a first network, which is called the generator, and the goal of this network is to generate new artificial data from a small source of entropy. And the second network called the discriminator, the second network is called the discriminator, and the goal of this network is to be able to distinguish between the real data example and the artificial data generated by the generator network. So both networks are trained in parallel, and actually they are competing against each other. And so ideally, what happens at the end is that over time, the generator becomes so good at generating new data that the discriminator is not able to properly distinguish the real data from the fake generated data. And so one application of this is, for example, to use GANs to generate artificial data for what we call data augmentation. Okay, so in deep learning, usually the more data we have to train the network, the better. And so in deep learning, you have a technique, a set of techniques which is called data augmentation, where the idea is to, from a small or limited data set, we artificially increase the size of the data set to improve the overall performance of the network during the training. And so GAN, generative adversarial networks, it provides a way to generate this type of artificial data. And so it's an interesting technique for data augmentation. And so below, I listed one article from 2021, which explores this type of technique for data augmentation in the context of side-channel analysis. And again, it's pretty interesting. And so that's it for today's presentation. I hope this talk gave you a good overview of how and why deep learning is really changing the way we perform side-channel analysis, and why it's one of the most active topics in this field today. Thanks a lot for listening, and I will see you next time.